Welcome to Evidence Mastery with Dr. Massoud Toussi. Today, we're diving into a brand new explainer on metadata, ontologies, and standards. We're going to unpack the essential underlying infrastructure of health data. Look, whether you're a professional in pharma, healthcare, academia, sitting at a regulatory agency or HTA body, or even a student just stepping into the field, understanding this structural foundation, it's absolutely critical. Here on Evidence Mastery, we're all about transforming really complex real-world data concepts into clear, actionable knowledge. Our main goal? To empower you to navigate the real-world evidence landscape with absolute confidence. Let's get right into it. We've got a really clear roadmap for today. We're going to cover why metadata matters, standardizing clinical terminologies, interoperability and data models, dictionaries and codebooks, and we'll wrap up with mapping and harmonization challenges. All right, Section 1. Why metadata matters, the context of data. Picture this. You're looking at a raw lab value in a database, and it just says 120. Well, by itself, that number is completely meaningless, right? Is it 120 milligrams per deciliter? Is it a fasting blood glucose level? Maybe a heart rate? What specific assay was even used? Without knowing the unit of measurement, the analyte, or the timing, you literally cannot use that data for any serious scientific inquiry. And this is exactly where metadata steps in. It's essentially data about data. In health research, it gives us three critical domains to save our data sets from total ambiguity. First up is context. What does this data element actually represent? Like, is it date field the date of a diagnosis, or just the date a billing claim was submitted? Second is provenance. Where did this data come from, and what transformation rules were applied to it along the way? And third is interpretability. This allows secondary users, meaning researchers who had nothing to do with the original data collection, to actually understand and reuse the data reliably. This whole concept perfectly illustrates the classic garbage in, garbage out paradigm. Without comprehensive metadata, you are risking massive failures. For instance, a classic example of this happened in early multi-center oncology studies. Researchers recorded tumor size, but they completely failed to include metadata specifying the measurement methodology. Was it the longest diameter, a volumetric calculation? Was the image an MRI or a CT scan? Because of this missing semantic context, the pooled data was rendered entirely unusable for rigorous comparative effectiveness research. They were forced into incredibly costly retrospective chart reviews just to reconstruct that basic context. Ouch. Moving right along to Section 2. Standardizing clinical terminologies, achieving semantic interoperability. Because to avoid that exact garbage-in scenario we just talked about, we absolutely have to map our raw data to standardized vocabularies. So what is a clinical terminology? Simply put, it's a structured, controlled vocabulary of clinical concepts. It ensures that we represent clinical information consistently, no matter what health system, clinic, or even country the data is coming from. Every single concept gets a unique identifier, a standardized name, and defined relationships to other concepts. This is what allows totally different systems to exchange data with an unambiguous shared meaning. Now, when we compare two absolute heavyweights in clinical terminologies, SNOMED CT and ICD, the differences in clinical nuance really become clear. SNOMED CT is an ontology specifically designed for the point of care. It offers incredibly granular, hierarchical clinical detail, so it can separately code something like type 2 diabetes mellitus and diabetic nephropathy and actually link them together with causal relationships. On the flip side, ICD, or the International Classification of Diseases, is primarily designed for billing, reimbursement, and mortality statistics, so it often lacks that deep clinical nuance, and it tends to group those complex, distinct concepts into a single classification code. Both are super vital to the ecosystem, but they serve very different analytical purposes. But it's not just about diagnoses. We also rely heavily on specialized standard terminologies for other things. For instance, we use LOINC to standardize medical laboratory observations. Think about mapping thousands of proprietary local hospital codes for hemoglobin A1C into just one universal LOINC code, a real game changer. And then for complex medication data, which, by the way, is absolutely critical for pharmacovigilance, we use RxNorm in the United States to normalize names for clinical drugs. Globally, we use the ATC classification system to categorize those drugs based on their therapeutic and chemical characteristics. Which brings us to Section 3, interoperability and data models, structuring the exchange. You see, while clinical terminologies give our individual data elements shared meaning, interoperability standards dictate the actual structure and format used to exchange and store them. So, the absolutely crucial piece of the puzzle here is interoperability. It's the ability of completely different information systems, devices, and applications to access, exchange, integrate, and cooperatively use data in a coordinated way. True interoperability allows this seamless exchange to happen across organizational, regional, and even national boundaries, basically tearing down the traditional, frustrating silos of healthcare data. The global landscape of interoperability is currently dominated by 3 massive frameworks, and each one is tailored for a very specific use case. First, there's HL7 FHIR. This is the modern, web-based standard for transactional exchange. It's the engine that powers real-time data movement and those patient-facing health apps you probably have on your phone right now. Second, we have the OMOP Common Data Model, maintained by the awesome OHDSI community. This is a relational database schema optimized for massive, retrospective, observational research. It literally lets a researcher write a single query once and then run it across hundreds of global databases without changing a line of code. Incredible, right? And finally, CDISC is the gold standard for structuring data for rigorous regulatory submissions to agencies like the FDA or EMA, ensuring that our real-world evidence meets the exact same formatting standards as traditional clinical trials. Okay, let's look at Section 4. Dictionaries and codebooks, navigating the dataset. Because even if your data is perfectly standardized and structured within a common data model, you still need accessible documentation so researchers can actually navigate the thing. And that is exactly where data dictionaries and codebooks come to the rescue. These are centralized repositories and detailed documents that spell out the meaning, data types, permissible values, and mapping algorithms for every single data element. Think of these documents as the essential bridge between the highly technical database schema engineered by the IT folks and the clinical researcher who's just trying to draw actual medical insights from the dataset. To put that into perspective, take a look at this representative excerpt of an oncology data dictionary. Every single variable has strict rules. Take tumor stage, for example. Its permissible values are explicitly limited to standard stages, and its source mapping rule explains exactly how it was extracted using a natural language processing algorithm. Or look down at treatment start date. The mapping rule clearly dictates it's derived from the earliest date in the pharmacy administration table. Everything has to be explicitly defined like this if we want to maintain serious scientific rigor. Now for Section 5, Mapping and Harmonization Challenges, the reality of real-world data. Because let's be real, transforming raw, heterogeneous, and often incredibly messy real-world data into these beautiful, standardized models, it's rarely a smooth process. We call this whole transformation process data harmonization. It's the act of bringing data from multiple, completely disparate sources into a common format, structure, and semantic framework to enable integrated analysis. Conceptually, super simple to understand, but in reality, it remains one of the most resource-intensive, headache-inducing, and error-prone phases of engineering real-world data. We are constantly running into mapping ambiguities. Why? Because actual clinical practice is highly nuanced, while standard terminologies have to be generalized. We constantly face many-to-one scenarios, like trying to condense 15 distinct local hospital codes for minor variations of a lipid panel into just one broader LOINC code. Naturally, that results in some loss of clinical detail. Conversely, we face one-to-many challenges. This is where a single basic local code for diabetes has to be split into multiple complex SNOMED CT codes depending on the specific patient context. And as you can imagine, that requires some very complex conditional logic in your data pipeline. We also have to navigate the temporal evolution of standards. Basically, terminologies aren't static. They change and evolve as medicine advances. A massive example of this was the October 2015 transition in the US from ICD-9 to ICD-10. Overnight, a single ICD-9 code for asthma exploded into dozens of highly specific ICD-10 codes. This transition severely disrupted longitudinal claims data. It forced researchers to build incredibly complex crosswalks just to ensure their patient cohorts remained consistent over time. And then, of course, there's the wild reality of semantic drift and local custom codes. Just imagine an electronic health record system that historically used a random custom code, say 999999, to specifically mean a patient refused a medication. If a researcher isn't aware of that local quirk, and that code isn't carefully harmonized during data extraction, the system might just drop the record entirely or flag it as an unknown event. And boom, you've instantly introduced a dangerous missingness bias into your study.
So with all that said, how do we actually manage these immense challenges? Well, frameworks like the OMOP Common Data Model utilize a dedicated source-to-concept map to document every single local code and its standard counterpart. Furthermore, communities like OHGSI use an incredible open-source federated curation process. Instead of every single hospital working in a silo, the global community collaboratively researches, flags, and standardizes unknown local codes together. It's a massive team effort that vastly improves data consistency across international research networks.
By the way, this entire explainer is based on foundational content from my upcoming book, Real World Evidence, Sources and Solutions, which is going to be available later this year. I highly encourage you to subscribe to the channel right now so you don't miss out on many more explainers just like this one, all focused on identifying, evaluating, and mastering real-world evidence and real-world data. I'll leave you with this final provocative thought to ponder. Now that we've put in all this monumental effort to perfectly standardize and harmonize this data, how do we safely, securely, and accurately link these disparate records across completely different systems? How do we form a comprehensive patient journey without violating privacy or introducing linkage bias? Well, we're going to be tackling that exact challenge next time. Thank you so much for learning with us today.